Hi guys, this was originally supposed to be the first video of the IB part of the channel, but I'd like to welcome you nevertheless to IB Physics. So today we're going to do A1 Kinematics, and we're also going to cover vectors, equations of motion, and projectile motion. First, I'd like to distinguish between scalars and vectors. Scalars are a physical quantity with only magnitude and no direction, examples being mass, distance, time, and temperature. Whereas vectors are a physical quantity with magnitude and direction. This includes velocity, displacement, force, and acceleration, and so on. So a thing that made the distinction clear for me was this racetrack I've drawn here. I know it doesn't really make much sense, maybe, but here is distance that the runner or whoever took from start to end, and it's distance, it's only magnitude measuring how far they've gone rather than in a specific direction, whereas the vector here, displacement in blue, has one direction and it measures the magnitude of only that direction. And you can remember it like that. So very quickly, how vectors are represented and how I can interpret them. Here is a green hypothetical vector. So we can split this down into two components, the horizontal and the vertical, making a nice triangle like this. You will need to do this for force diagrams and just force manipulation, which we'll cover a bit later on. And the vector here, the magnitude, is just the hypotenuse of those two. So as I've written here, it's the square root of the horizontal component squared plus the vertical component squared. And because it also has a direction, usually have theta here to the horizontal, and you can work out either component or the magnitude or theta as well using SOHCAHTOA and basic trigonometry. So I'm also going to cover multiplying vectors and adding them. First, for multiplication, we have a hypothetical vector A here with horizontal and vertical components of B and C respectively. So if you multiply, for example, by 2, you just put these two one on top of each other, where here the stick part, the end, touches the arrow of the previous one, and it just multiplies the horizontal and vertical ones by the same amount you've multiplied the normal vector by. And obviously, you also double the magnitude in this case. But theta here is still the same. So these two are just like similar triangles. Similarly, in minus A, you would just turn the arrow the other way around and make the horizontal and vertical components the negative version of the original. Adding vectors is also pretty simple. You just have to make sure that you draw an arrow and then start the next one where the previous arrow finished, and do it like that rather than, for example, doing this and putting both arrows like that, because then you get resultant vector like this, and that is wrong. So just bear in mind you draw it like this. Then we have a little car that I've drawn here, and this is an example of a question you might be able to do in an exam where you have to add vectors. So we have thrust probably from the engine of 50 newtons going forward, and we have a frictional force of 5 newtons going back. So the first step in doing this is to choose a direction to compare all the other forces to. So in this case, I would choose the forward direction like this, So we do 50 here is positive. But then, since the 5 newtons here is in the opposite direction, this would be minus 5. So then in step 2, when you make a formula, and in this case you want to work out the sum of the forces or the resultant force, you can then just put 50 and then minus 5 because you've already worked out the signs, and you work out 45 from that. Then the last steps, you have to always check for plausibility. So compare to the figures in the question or what you feel would be roughly right. In this case, I would say it feels about right. And then always remember your units, newtons, because you would lose a mark otherwise. But yeah, units. Then an example of adding vectors together. Here we've got A, B, and C, and you would add them up like this, starting one to the arrow, then you start the next one from the previous arrow leading to the next arrow, and you work out the resultant force here by starting from the start of the first arrow and the head of the last arrow like that. Then moving on to motion, we have S, which is displacement. So final position minus initial position. Remember the racetrack from before, it's not all the way around, it's just the start minus the finish. Then we've got velocity, which is the change in displacement over time. You can work out speed, which is the scalar version of velocity, using the change in distance over time. And then we've got acceleration, which is the change in velocity or the change in speed over time. These aren't in the data booklet, but you should know them anyway. Moving on to distance time graphs, we have displacement on the y-axis and time on the x-axis. The gradient for this, you should know, it will be velocity. If you imagine working out the gradient normally in maths, it's delta y over delta x, and substituting in what's on the y-axis and the x-axis, we get delta s over delta t, which we know is velocity. From this, we know that the steeper the gradient, the greater the velocity. Then we've got velocity time graphs, which, working out the gradient the same way, is now equal to acceleration. So again, steeper the gradient, the more acceleration there is. But you can also work out the displacement using this graph, and you simply work out the area under the curve. So the larger the area under, for example, between time 1 and time 2 here, the distance or displacement would be this. And just a thing to note, gradient and area can be negative because velocity and displacement are both vectors and can therefore be negative if it's in the opposite direction. Now, we also need to be able to work out average velocities and instantaneous velocities, or also accelerations. So the average velocity, you are just interested in the initial displacement or time and comparing that to the final displacement and time. You just substitute that into the normal equation for velocity, calculating the difference between the two first and dividing them. But then for the instantaneous velocity, it's a little more complicated. You have to first draw a tangent at the time that they want here, for example, at t. You have to draw a tangent and then substitute for delta s and delta t the different components of the tangent, but not too complicated. Now, equations of motion, or more commonly known as SUVAT, which are the equations of motion for uniform acceleration. They're called SUVAT because these are the 5 characters that appear in these equations. S, as we know, is displacement. U is initial velocity. V is final velocity. A is acceleration. And T is time. So here on the left are the 4 SUVAT equations. These are in the formula booklet, so you don't need to know them off by heart. And then here we've got a question. If you want to work it out by yourself, just don't look at the answer. But it's a car is traveling at 3 meters per second. It accelerates uniformly for 8 seconds and reaches velocity of 9 meters per second. What is the total distance traveled in these 8 seconds? Now, the first thing I would do with this question is identify all the information they've given us. So first, what are they asking? They're asking for the total distance or displacement. So I would write S with a question mark to remind ourselves that's what we're looking for. Then we've got U, which they've told us in the question, is 3, V is 9, and T is 8. Second thing, immediately I would look at the units that they've provided in the question. In this case, it's meters per second and seconds, which are the base units. But just in case they give you, for example, kilometers per hour or minutes, you just have to convert those then into these base units. Then I would find the equation that fits all the information you're given or looking for. In this case, it's S is U plus V over 2 times time. And substitute in the numbers and get an answer. And then you round it to the same number of significant figures as in the question. And don't forget units. In this case, it's meters. And you get 50. Great. Moving on to projectile motion. This will usually involve balls or cannons or stuff like that, where they'll say that someone threw a ball in the air at so many meters per second, and there's 3 questions that they like to ask you. Maximum height, total time in air, and horizontal displacement. So let's attempt something. Again, if you want to try it yourself, don't look at the answers, but we're going to go through it. A ball is kicked at 30 degrees from the horizontal with a speed of 25 meters per second. What is the maximum height? And now, I drew a little vector here, like the one before. We have 25 as the magnitude of it, so the hypotenuse, and then we've got 30 degrees here. Now, for the maximum height, we want the vertical velocity. So I've labelled that here on the components. And using trigonometry, we figure out that the initial vertical velocity is 25 times the sine of 30 meters per second. And we have the acceleration because we know what gravity is on Earth. And we take that from the data booklet, which is minus 9.8. The minus is there because it acts in the opposite direction, because the vertical velocity here would be acting up, whereas the acceleration would be acting down. And then we know that at maximum height, the vertical velocity will be 0 because it's just about to go back down. Now, looking at the information here, we know that the equation we need is v squared is u squared plus 2as. Now, rearranging for s, which is what we're looking for, we substitute in everything and we get 7.97. And we round that to around 8 meters. Don't forget the units. Then moving on to working out the total time in air, we again use the vertical velocity initial which is 25 sine 30. Then we've got the final vertical velocity, which is minus 25 sine 30, because we know that when it hits the ground again, or just before it hits the ground, it will have the same vertical velocity, just downwards instead of upwards, because it's gone the same way up and down again. And then again, we have the acceleration of minus 9.8. Then checking all the base units, they're all fine. So I'm going to go ahead and plug that into v equals u plus at. Rearrange it a bit, and then we get approximately 2.6 seconds, and that's good. Now, the horizontal displacement. This time we also need to work out the horizontal initial velocity, which is using trigonometry again. 25 cos 30. Then we know that the acceleration of this is 0 because there are no forces acting on the horizontal plane, so the velocity is constant. So we know also that the final horizontal velocity is 25 cos 30. And as we've just worked out from the previous question, we also know the time that it's in the air for. So then we go ahead, choose the equation that we want, which is s equals u plus v over 2 times t, and substitute in all the numbers, and we get about 55 meters. Good job. Now, projectile motion fluids is a little different compared to when it's in a vacuum, or if we assume there is no air resistance. So here's a quick graph here comparing vertical distance and the trajectory of the balls with and without air resistance. You can probably see from my terrible graph that in the one with air resistance, the trajectory is no longer parabolic, so it's not really symmetrical completely. The maximum height is lower, the range is lower, the velocity is lower, and the time that it is in the air for is lower. And that brings us on to terminal velocity. So here we can imagine a parachutist. At the start here, he has a velocity of 0 because he's just more or less stationary on a plane. Then as soon as he jumps out, his acceleration increases and his velocity increases, but the acceleration is getting less and less because the air resistance is more, until it reaches final velocity, or terminal velocity, number 1. When someone reaches terminal velocity or something, it means that the frictional forces or the drag are equal to the force of weight or gravity, and therefore there is no resultant force and the velocity remains constant. Then we see here a point where the parachutist then opens the parachute and decelerates very quickly, and then at a decreasing rate until terminal velocity 2 is reached, when the drag and weight are equal again, and then the parachutist lands. So yeah, that was it for kinematics. I hope you found it interesting or useful. Have a great day.